Students, this is one of my favorite lessons on fossils, because fossils are so fascinating because you can find them even around here. Our reflective journal question, which I want you to answer before instruction, is how can we tell how old a fossil is? When we find a fossil, how can we tell the age of it? That's going to be your before instruction answer. Don't worry about your answer, just answer to the best of your current knowledge. I've got a few fossils here and a couple of articles. This is about a couple little boys that live in the Detroit area who were just playing by the river by their house, and they found a mastodon bone. 10, 12,000 years ago, there were mastodons roaming this area. In fact, they often, when they're digging roads, they will often find teeth or pieces of skull. But these guys found looks like a pelvic bone or some kind of bone, and it's about 13 to 14,000 years old. And later in the lesson, we'll see how they put that age of 13 to 14,000 years old. We know there were mastodons in this area 12, 13, 14,000 years ago. In fact, we have the best mastodon tracks in the world at our Museum of Natural History in Ann Arbor, which is free, which youngsters, from the age of 4 to 10 love natural history museums. They have all kinds of fossils, all kinds of specimens, and little kids just love fossils. Now, this was an interesting find. There was a woman in Britain that just made it her lifelong ambition to find the bones of King Richard. She knew about where he was killed and how he was killed, and she just pursued it and pursued it and pursued it, and actually talked either the British government, some company, whatever, into digging in this one parking lot, and lo and behold, she found the skeleton of King Richard, which is much more recent than these mastodon bones. But King Richard, as you know, had scoliosis. And they also found the wound in his shoulder from a spear, and I think there was also a wound in his skull. This is a living relative of King Richard, so they even did DNA testing to make sure that was him. Fossils are so fascinating. Back in the day, let's see, 200 million years ago, oysters were this huge. Through natural selection, oysters have been selected for being much smaller. But at one time in history, oysters were massive like this. These are fossilized oysters. At one time in our natural history, dragonflies, it was an advantage to be 7 feet long. Imagine if selective pressures hadn't acted on dragonflies and they were still 7 feet long. That would be scary, wouldn't it? But fossils just tell us a story about how the Earth was. Now, I'm going to make a disclaimer here that some of you with times of the Earth might think that the Earth is 6,000 years old because that's what you've been told, that's what you've been taught. When you are teaching science, you have to teach science. So I myself am a Christian. I go to church. My colleagues in the science department here, we have Jewish colleagues, Muslim colleagues. I have Buddhist colleagues. Most every one of my colleagues, except for a few, all worship their God. They all, have a spiritual life. But when it comes to science, they also go by what we find in science and not what someone told them to think. Okay? Even this mastodon, and on Canvas, there's another video of a mastodon that was found in Chelsea by a farmer that's also 12,000, 14,000 years old. We can accurately age them that old, so we know for a fact the Earth is more than 6,000 years old. So please just kind of look into things. God and your spiritual advisors, they tell you how to live your life, how to be a good person. don't look to them for scientific fact, because it's kind of a different thing. So that's my little disclaimer. All right, here we have a bunch of Petoskey stones. The Michigan State stone is called the Petoskey stone, and it's actually a coral. At one time, Michigan was covered by oceans, and these are actually coral. We know there was a marine environment because there's coral right here in Petoskey, Michigan, Traverse City. You can find these on Lake Huron and Lake Michigan, and they come out. When you find them on the beach, they're kind of rough, but then you can polish them, and you can put different finishes on them, and you can get these nice shiny things. You can get a nice Michigan mitten made out of Petoskey stones, nice earrings. You can get all kinds of cool things. When you go up north to the gift shops, they often have Petoskey stones in there. So we know that there's all kinds of fossil evidence in the ground. Now, our question is, how can we tell the age of them? And so our first explore is going to be for your group. So you're going to be working in your groups on your Google Doc. And your group is going to, by looking at these rocks, and I'm going to have other groups of rocks as well, what I want you to do is put them in order from youngest to oldest. So you can say rock 1 and you can describe it, or you can put a picture, whatever you want to do. When I put the assignment in, I'll actually take pictures of the rocks and I'll have them A, B, C, D, E. And you're going to order them from youngest to oldest based on their characteristics. So that'll take you a little while, and I want you to do that based on what you see. Maybe you want to say, oh, plants were first, so this must be the oldest. Maybe you want to see this thing is not all worn down, so maybe you'd say that was the next oldest. You know Petoskey stones are from about 200 million years ago, so maybe you would choose that one. However you're going to do it, I want you to order these in order of appearance or age. Okay? Now, how can we really tell how old a fossil is? There's two ways, relative dating and absolute dating. And we're going to talk about relative dating first. And I'm going to tell you a story about some fish. And these fish were living in an area, and we've got a river, or we've got some water, and we've got some fish. Okay. And like all living things, what eventually happens to the fish is that they die. And when fish first die, the bacteria start eating the bodies up. And the bacteria enjoy eating the bodies up. And they give off gases, and the fish will float. Eventually it will sink. And if it sinks in an area where it's buried quickly, we have the potential for fossils. Fossils are so rare. It's such a very tiny percentage of things that die that become fossils, because the conditions have to be right. There has to be a quick burial with sand or something else. Maybe they've got a river flowing into a lake and there's lots of sediment falling on it. And it has to have some hard parts. And that's why when we did our geologic time scale, there's so little fossils from the 2 billion years ago, because all the things had just soft parts. There weren't hard parts like skeletons or skulls or exoskeletons or whatever. So let's say these fish die, and they eventually will sink, even though they float first. And so we have a layer here that has some dead fish. Okay? They were buried quickly, and they became fossils. We've got some other critters. I don't even know what I'll call these, just little urchins. Okay? And these things were living, and they died. And maybe there was a fish also at that time. This layer has some urchins, and it has some fish. And so as you see, over time, we will get sediments burying. We will get fossils being formed, and they form in layers. Another layer forms here. So if I was to label these, if this is a lake in Michigan, I would call this M1, and I would call this M2, and I would call this M3. 1 being the what? Would this be the youngest layer or the oldest layer? Which one is the oldest? Which one is the youngest? Okay. This is the most recent, so this would be the youngest layer. M3 would be the oldest layer. So this is one way, this is relative dating. In other words, we date the fossils based on what layer of the earth they're found in. So we're going to take our second can, which has various fossils in it. Now they're in bags, and each of these has a letter and a number. The letter says where it was found. For example, Michigan 3. Okay, this would be Michigan 2. All right. So we've got lots and lots. We've got R. Let's say that's Rwanda 1. Okay. This is Michigan 1. Okay. Y. Let's say Yemen 2. So the letter tells where it was found. The number tells what layer it was found in. Okay. We've got some U's, so we have Uganda. We have lots of bags in here. Now, each of the groups is going to get their own set of bags. And what you're going to do is figure out of your fossils, which one is the very youngest and which one is the very oldest. So it's easy to do that in Yemen. We've got Yemen 2. Below it would be Yemen 3. And now we find Yemen 1. No problem. That was easy to put these in order. Yemen 1, Yemen 2, Yemen 3. Now, how do we relate the Michigan fossils to the Yemen fossils? So quite often we can make relationships. We can use what's called an index fossil, which is a fossil that was widespread around the whole world and lived for a short period of time, and we can kind of tell, oh, now I can make a correlation between Yemen and Michigan. Now, this fossil here, and I'm sorry you can't see these as well, the ones you're going to do, I'm going to take pictures close up so you'll be able to tell what they are. This one here does not match any of those. I'm going to try to find something that matches one of the Yemens. Okay, so I'm looking for a match. I'm looking for something that looks exactly like, oh, and I've got a match right here. Uganda 1 is an exact match to Yemen 3. So we can say that these fossils were found in the relatively same time. Now, I've got Uganda 1 here. Where would I put Uganda 2? And where would I put Uganda 3? Here's Uganda 2. Where would Uganda 2 go? Uganda 2 is going to go under Uganda 1, because remember, they're in layers. We're doing it in layers. Uganda 3 would go under Uganda 2, and Uganda 4 would go. So what I've done so far is I've related the fossils in Yemen to the fossils in Uganda. Now, out of all the fossils that are down here, which one would be the youngest? It would be Yemen 1. Yemen 1 would be the youngest. Uganda 4 would be the oldest. Okay. How do I know that? Well, I know that Uganda 1 and Yemen 3 are the same, and so I know this would be older and this would be the youngest. Now I've got to find another match. This gets a little complicated. Michigan 1 looks like an exact match for Uganda 2. Filling in the rest of the Michigans is easy. Michigan 2, Michigan 3. Whoops. And it looks to me like Michigan 3 and Uganda 4 are exactly the same. So what you have to do is relative to the others. When you find a match, put those two together. Put the other members of that column above or below where they're supposed to go. Out of what I have right now, we've got Michigan 3 and Uganda 4 are the very oldest. Yemen 1 is still the youngest. Okay? So you are going to have a group of fossils. I'm going to have pictures of them, and you are going to order them according to which one's the oldest, which one's the youngest, and put them. This is called the law of superposition. This is called the law of superposition. So let's look at that. Again, this is a relative way to date things. The oldest rocks are on the bottom. The oldest rocks are on the bottom. So within Yemen 1, 2, and 3, which ones are the oldest? The oldest rocks are on the bottom. Yemen 3 would be the oldest. Okay. Michigan 3 would be the oldest. It's a very simple law. And remember, laws in science are just things we observe. The law of gravity, we observe that when we drop something, it falls to the ground. That's the law of gravity. The theory of evolution, or the theory of plate tectonics, is the best explanation we have right now for that particular topic. So the theory of evolution is our best explanation for how life changed from the beginning of time, from the beginning of life. The theory of evolution has nothing to do with the origin of life. Nothing. It's simply lots of lines of evidence that tell us how things evolved. As I was saying in the beginning, how the dragonflies used to be 7 feet. At one time, it was an advantage for dragonflies to be 7 feet long. Through natural selection, which is one mechanism of evolution, dragonflies are now just a few inches long, thankfully, because a 7-foot dragonfly would be quite scary. Right? The law of superposition, just stating the oldest are on the bottom. Within your set that I give you, you are going to order them from youngest to oldest. Now, the principle of original horizontality is basically the same as the law of superposition. Just says that sediments are deposited, horizontally. So like in our example in the lake, the sediments are deposited horizontally. Now, if a mountain is built in the middle of that, or there's some kind of tectonic activity, all bets are off with this. Now, the next principle of cross-cutting relationships, this is a very important topic for your exam. Okay? When you look at this figure, we say the law of superposition says that this would be the oldest layer, next oldest, next, and that this layer on top would be the youngest layer. That's the law of superposition. Now, cross-cutting relationship says, as we see, that the younger feature cuts through an older feature. So let me show you that again. A younger feature cuts through an older feature. So what would be younger, dike A or this column of rock? Well, dike A is cutting through the entire column. So dike A would be younger. When you look at dike B, however, dike B forms and then kind of levels out at this point. So if I was to ask you, is the conglomerate younger or is dike B younger? This would be the conglomerate layer. You would say the conglomerate is younger, okay? Because dike B is not cutting through it. Now, if I asked you, is the sandstone younger or is dike B younger? You would say dike B because it's cutting through the sandstone. So this is the cross-cutting relationships. You'll have a similar diagram to this. Now, if we look at this batholith, this is kind of interesting. What was there first? Was the fault there first, and then the batholith came after? And what these rocks are, these are all igneous rocks. These were all magma at one time. So there had to be some kind of little fracture, and the magma was able to slide up this entire column of rock. There had to be some way for the magma to get in there, and then while it was liquid when it came through here. These are all igneous rocks that kind of scoot in. Now, the batholith or fault B. Is the batholith cutting through fault B or is fault B cutting through the batholith? Which is younger? The batholith would be younger. The fault was there first, the batholith came after. They're going to throw diagrams like this on your Michigan teacher test, so that's why I'm putting that in there, just so you don't panic when you see something like that. Now, we have one last idea. So far we've only been talking about relative dating. This is another example of relative dating where you've got a unit of fossils. We know the approximate ages that all these fossils lived. So the only place this one intersects is right here. So we can say this was X number of years ago relative to the other things. Again, another example of relative dating. We are relating one to another, and that's a big argument of creationists who think the Earth is 6,000 years old, is that, well, how do you know when this column was formed or that column was formed? You don't give an absolute date. So how can you tell? You're just doing everything relative to something else, so you can't be sure about the numbers. But relative dating is not the only way that we can identify the ages of things. Okay? There's also radioactive or absolute dating. Okay? So the mastodon that was found in Chelsea, or the mastodon that these boys found, this bone, these were all dated using radioactive decay. In this case, because it is relatively young, it's only 13,000 years old, they were able to use carbon dating. Okay? There's two forms of carbon. There's actually more than two forms of carbon. We have carbon-14 and carbon-12. And while we're breathing, we have carbon-14 and 12 in our bodies. When we stop breathing, the carbon-14 that's in our tissues will begin to decay. The half-life of carbon-14 is 5,730 years. Okay? So this is how it works. When the living thing stops breathing, there are, let's just simplify it and say, there's 100 isotopes of the carbon-14. After 5,700, and I think it's 30, maybe 60 years, half of the originals have now decayed into another isotope. And so at this point, we have a 1-to-1 ratio between the carbon-14 and the decayed product. So they can take a scraping from this bone and find the ratio between the original parent isotope and the product, the daughter product. And if it's 1-to-1, they know it's 5,730 years, I believe. Okay, it might be 60. So with carbon-14, with things that died recently in the last, well, if you look, when you get down to the third half-life, which would mean the thing is about 18,000 years old, now you're looking at a like 1-to-6 ratio. Here, it's almost like a 1-to-18 ratio. It gets a little harder the older something is if you're using carbon-14. Fifth half-life, you'd only have 3 to 97, like a 1-to-20 whatever ratio, so it's a little harder. So we use carbon-14 for things, actually, if it's less than about 50,000 years old, we can use carbon-14 to date things. Now, the age of the Earth is in the billions. We can't use carbon-14 to date the Earth. We have to use uranium-235, which has a half-life in the billions. The way this works is we look at the ratio. In the beginning, it's all the parent isotope. As the decay happens, one half-life, a 1-to-1 ratio, if you were using carbon-14, that would mean that specimen is 5,700 years old. If it was a 1-to-3 ratio between the parent and the daughter product, then you would say that specimen is 2 times 5,730. If it was a 1-to-6 ratio, you would say it was 3 times, so it would be about 18,000 years old, and so on. On the exam, I'll tell you, an element has a half-life of 20,000 years, and there's a 1-to-1 ratio. If there's a 1-to-1 ratio, that means there's been one half-life. That means that particular fossil, whatever was found, is 20,000 years old. Okay? If it's a 1-to-3 ratio, that means that fossil is 40,000 years old. And there's a really nice 4 or 5 minute video put on by NOVA in our Canvas site that will explain all this for you. Okay? It'll really explain well how it goes. Now, you have now answered the question. Remember the original question? How can you tell the age of a fossil? The way you tell an age of a fossil is by relative dating. And I want you to discuss the law of superposition and absolute dating, and you will discuss radioactive decay or absolute dating. Remember, then you reflect on your learning. How did you learn that? And talk about the different techniques used. There will be many other exercises for you to do on the group assignment you'll do on fossils. And you should be able to answer that in a complete and scientific way.